Okay, so this is the crossed fields problem, right? These are famous problems that we all as physicists have to solve, right? What electric field in what direction would make the particle go straight up the page in the previous problem? Well, if in part 4 you drew a picture of it going up the page, this is what you had, right? This is our magnetic field, right? It's out of the page. That's what the little dots mean, right? And then this is our velocity. This thing is moving straight up the page, right? So that we take that to be the direction of the current, right? So that's our index finger. Index. There we go. Okay, so if I do this, if I put my index finger up the page, middle finger out of the page, right? This is my middle finger. Okay, then my thumb is pointing to the right on this page here. This is the direction of the magnetic force. Okay, so therefore, if we want to make this, if the magnetic force is the only force acting on it, then it's just going to make this thing go in clockwise circles, around and around and around and around and around. Okay, I don't want it to go in circles, so what I do is I cancel out that force with an electric field. So I'm going to have an electric force to the left. Okay. Now, since it's a positive charge, to exert a force to the left, the electric field really is to the left. All of these things are backwards for a negatively charged particle. Okay, but for this guy, if I want to exert a force to the left, my electric field is to the left. Very, very straightforward. Okay, and if it's an electron, they're both backwards. Okay. Okay, so ultimately what we do is we use the electric field is force divided by charge. That's in our data packet, and then force is equal to QVB. Right? So if I solve this for force, I get that the electric force is EQ, right? And I set that equal to QVB. And the interesting thing is that the charge cancels. Regardless of the charge, as long as it has charge, this electric field and magnetic field select for a particular velocity, which is, I think, fascinating, right? This is how they discriminate between particles going different velocities. If they have charge, you can make them go straight with a particular ratio of electric to magnetic field. Okay, all we have to do here is solve for E, which is just VB, right? So that's E is equal to 1.71 times 10 to the 5th meters per second, and our magnetic field is 2.3 Teslas, right? So 1.71 e to the 5th times 2.3. You have to multiply things, right? I'm getting 393,300, right? Okay, so that'd be 3.93 times 10 to the 5th. And that's newtons per coulomb, or Tesla meters per second. That equals a Tesla meter per second. Isn't that crazy? Little dogs. All right.